Alrighty. So the material that I'm referencing, again, is all in the content library. So the Chapter 1 materials are all in the content library. Today we're going to talk about sections 1 and 2. So again, you're welcome to take notes on paper, or you can sit and watch, or you can do it on the OneNote. Any of those things are fine. Anything that I write down in class is going to be in the content library on OneNote. We're recording the lectures, so if you're like, I do better just sitting and listening, and I'll kind of review the notes later, or if I need to write down everything the person says, wherever you kind of land. I think at 16, 17, 18 years old, or however old we are, that's your prerogative. You should hopefully by this age at least figured out something that works well for you, or at least doesn't work well for you, and try something different. And I'm not going to micromanage any of that kind of stuff for you. So section 1 here is all about functions. So we'll just start with maybe our most fundamental definition from Algebra 2, and that's the definition of a function. So we say a function that goes from a set D to a set R is a rule or a pairing such that every member of D pairs with exactly one member of R. And these sets D and R we refer to as the domain and range. So if you remember back from our Algebra 2 class, we had several different ways we could represent these functions, or more generally, a relation that's a pairing that doesn't meet this definition, as we just call it a relation. One of the first ones that we would talk about is a mapping diagram. So let's just look at a couple of examples of some mapping diagrams and decide which one of them represent a function, or which of them, I should say. So when we draw a mapping diagram, typically we draw two circles, one representing the set D and the other representing the set R. And we usually put a couple of points inside the circles representing the members of that set. More often than not, those members would be numbers. I'm going to write generically, though, I'm just going to label them as like x1, x2, x3, and y1, y2, y3. But in practice, this would be like one number paired with another number. And then what we do is we draw some arrows to show how the members of the set D are paired with the members of the set Y. So again, there's no reasoning as to why I've drawn the arrows in this way, just an example, so I've kind of drawn them arbitrarily. So we're going to take a look at our definition. If I can get my stylus to work again. There we go. Okay. We'll use our definition that we just wrote up previously to decide whether this looks like, or this represents a function or not. So what I need to look at is I need every member in the domain to be paired with something. So if I look, all three of the things in the domain have an arrow coming from them. So that's good. Every member is used. And then they have to be paired to exactly one place. So I'm going to check coming out of these x's to make sure that the x's are only going one place, which they are. So this is something I would say is a function. Everybody okay there? Let's do a couple more examples just to make sure we kind of get the idea here. But it's not too difficult of a concept, especially when you're seeing it for a second time. So how about this mapping diagram? Does this represent a function? No. Why not?
X3 doesn't have a partner.
Yeah, exactly. So the problem there is that not everything in the domain has a partner, is paired with something. Very good. And if I wanted to make this a function, what would I need to do? You know, x3 would need to go somewhere. If I added that in, then this would become a function. Does it matter that one of the y's wasn't used? No. Does it matter that one of the y's is used twice? No. The y's don't matter when we're determining whether something's a function or not. So all we care about is what's happening at the x's. So again, if I add that one in blue, that would then become a function. And again, my stylus is, there we go. Okay, one more example, and we'll move forward to a different representation. So how about this one? Is this representing a function? No. What's the problem here? Good. X1 is being used twice. It's going to two separate locations. So this would be not a function. If I wanted to turn this into a function, what would I have to do?
Get rid of one of the pairs of X1.
Yeah, get rid of one of the pairings using X1. So like if I got rid of that one, say, that would in turn then be a function. Does this all feel relatively familiar? Ringing some bells, I'm hoping. Again, if you weren't a pro at the very start, at least you're like, okay, that jogged my memory a little bit and this is coming back to me. It's kind of the minimum that I'm hoping for. If you're like, yeah, I remember doing this before, that's excellent. If you're like, oh, well, it's ringing a bell, that's good enough. Again, we're going over this again, and it's something we've done before, so it should be coming back to you. Let's look at another representation that we could have. Maybe we ask, another representation we have is with, for a function, might be an equation or a formula. So we ask here, does the formula y equals x squared plus 2 define y as a function of x? So this little phrase at the end is interesting, right? What is this really telling us or implying to us? All it's doing here at the end is being very specific about which variable is the independent, which variable is the dependent variable. Now, when we look at y equals x squared plus 2, we would assume that y is the dependent variable and x is the independent variable, right? That's the way we've always written things in our Algebra 2 class, where we pick values for x and then we find the value for y. Everybody's remember doing that? And that's all that at the end is saying. It's just being specific and saying y as a function of x is saying that y depends on x, making it the dependent variable and x the independent variable. Everybody's okay with the wording there and what it's saying, or what the information it's conveying, I guess? Okay, so is it easy to look at a formula and tell it's a function? No. Is there another representation for that formula that might make it easier to tell if it's a function?
Graph.
Yeah, looking at its graph would be much easier to tell if it's a function or not. So if I look at y equals x squared plus 2, what kind of function is that? Or what kind of formula is that?
Slope, right?
Well, it's not a linear equation. It's not a slope-intercept equation because it has an x squared in it and not a 2x. If it was 2x plus 2, that would be linear. It'd be a slope-intercept equation. But this is x squared.
So it's exponential?
It's not exponential. If it was 2 to the x, that would be exponential. We spent a lot of time dealing with these last year.
Quadratic?
It's quadratic.
Yeah.
So if you have an x squared as your biggest degree, you have a quadratic polynomial. What shape is the graph of a quadratic polynomial? Do you remember? There's a name for that shape. It's a parabola. And a parabola is basically just looks like a U, right? So either the U is going to open upward or it would open down. Do you remember how to tell from the formula which one it's going to be?
Is it if the two values negative or positive?
So it's not the 2 being
The H.
positive or
Is
negative.
that what it's called?
It's the leading coefficient,
Oh.
positive or negative. Here the leading coefficient is 1, but that's positive, so my parabola should open up. The 2 at the end is going to tell us kind of where the y-intercept is. So this is just going to be, if my stylus wants to continue working, which apparently it wants to fight with me today. There it goes. So it's going to look something like this. Again, we don't need a hyper-specific graph to tell if it's a function or not. We just need a sketch, like we need thereabouts. Now, if what we did here was like, I wouldn't have remembered any of that, what else could you do to get a picture of the graph? Put it in your calculator and graph it, right? You could do that, and that would give you a reasonable picture if you weren't able to recognize this is a quadratic, so it's going to look like a parabola. If you're like, I would not have been able to do that, that's okay. The calculator can. And we'll take some time here this semester and kind of review how to do that stuff again. If you're like, I don't remember how to even do that. I remember I could do it last year, but now I'm not so sure. Okay, so we have a new representation here. We have a graph. How do I tell if a graph represents a function or not? If every x has one's y, or a vertical line test, right? So if I can draw any vertical line and it intersects the graph more than once, that would mean that it's not a function. But if I look at this, no matter where I draw that vertical line, it only hits the graph one place, right? So this would be a function. Everybody feel good with that? So again, once I have the graph, telling whether it's a function or not is usually pretty easy because that vertical line test is easy to do because it's all visual. It doesn't require any kind of computation at all, right? Which is sometimes the best stuff. Okay. What if I have something like this? Is that a function?
No.
No. So it should be easy to see that, hey, there's lots of places where I could draw a vertical line that'll intersect the graph more than once. Does it matter that, like, hey, there is... Gosh, come on, pen. Does it... No, you were just working a second ago. Does it matter that there is places where I can draw it and intersects just one time? No. No. All it takes is one... Come on. All it takes is one place where we intersect the graph more than once to make it not a function. Okay, so we've talked about mapping diagrams, we've talked about equations or formulas, and we've talked about graphs as three representations. The last way we represented a function, or that we talked about, was using function notation. Which was like y equals f of x. And what this is really saying, or what y equals f of x represents, is it's saying that y is the value of the function f at x. In all reality, it's not much different than just saying like y equals and then the formula. The advantage of using function notation is it's explicitly telling you which variable is the independent, which variable is the dependent variable. So whatever is inside our function here, come on, there we go, is our independent, and whatever's out here is always the dependent variable. So you don't need a phrase at the end to clarify which one is the independent or dependent variable. It's like baked into the function notation, which is nice. The other thing it can do is if I have a specific function, I can talk about, okay, well, what is the value of the function when I plug in, say, 2? But instead of having to use a sentence like that, I can just write it like this, right? F of 2 is the value of the function when we input 2 for x. So when I actually evaluate that, when I plug the 2 into my function, I get 2 again. And what this says, it says that 2, 2 is a point on the graph of f of x equals 3x minus 4. Everybody's kind of remember doing that? Again, that's just a notation, but one of the things that can make math kind of overwhelming for us is that there's a lot of notation, and if we don't really understand the meaning of things, you can lose a lot of the, the key concept or the big idea. And if you do that enough, things get overwhelming and it just stops making sense a whole lot. So I want to make sure that we take some time and kind of discuss what the notation is really saying. And we're really clear about that so that that doesn't end up happening. As an aside, the other way you can think about function notation is if we go back and think about our mapping diagram. So here's our x and here's our y. The set of instructions that tells us how to turn f into y is a function. It's called f. So that means that y is really, hold on, there we go, the transformation of f into x, right? We do some set of instructions to x and it turns into this y. right? That's the other way of kind of thinking about what this function notation is really representing. It's the information from a mapping diagram. Where it's like, okay, we start off with this value x, we did some set of instructions, and we end up with this value y. The set of instructions is the name for our function f.
This is all over the ACT.
Yeah, yeah. If you're if you're a junior this year, a recent junior, and you are in ACT prep points, this is normal ACT stuff that you'll likely see. Yep. Good point. That's kind of closes us for section 1. Section 2, as soon as my pen wants to start working again. Oh, there it goes.
How many sections are we doing today?
We're just going to do 2 today. Yeah. We're going to talk about domains and ranges. So if you remember back from our definition of a function, the domain and range were both sets, right? One way to represent a continuous set is with something called interval notation. Now, I said a whole bunch of words there. When I say a set, we're just talking about a group of numbers where nothing in that group is repeated, right? So like 1, 2, 3 is a set. Everybody's okay with that? Or everything between 1 and 2 is a set. So like 1.1, 1.01, 1.001, etc. All that stuff all the way to 2 would also represent a set. 1, 2, 3 is a discrete set because it just contains, standalone numbers. There's nothing like everything in a row. The second set, everything between 1 and 2, is a continuous set because you have all the decimals in between the two numbers. Is that okay with that idea when I say discrete versus continuous? So like if you were to plot these things on a number line, the discrete is just going to be a bunch of dots if I'm plotting a discrete set on a number line. A continuous set's going to have like a filled in line where you have everything from like 1 to 2. Okay with that? So interval notation is something we'd use to describe a continuous set. This is primarily what we would have done in our Algebra 2 class to describe domains and ranges when we talked about functions. Because in our class, or at the high school level, all these functions are continuous, or at least partially continuous. So let's talk about interval notation, because this is our main tool in this class to describe domains and ranges, or even sets. So the interval notation is formatted as follows. It's a lower bound and then a comma with an upper bound. And I'll describe what I mean by lower bound and upper bound in just a moment. And then around the lower bound, you'll either have a parenthesis or a bracket. And the same thing at the at the upper bound, you'll have a parenthesis or a bracket. The parenthesis indicates that that lower bound, that number that's the lower bound, is not included in the set. And that would frequently be because the set relationship involves a strict inequality, a less than or greater than. The bracket means that that lower bound is included. So it would have likely been part of a relationship of less than or equal to or greater than or equal to. And the same thing goes at the upper bound end. I'm not going to rewrite all that information, but the parenthesis and the bracket mean the same thing there. Okay, so let's start by doing some specific examples to reacquaint ourselves with this notation, but I think for the most part, Most of us use this notation throughout our Algebra 2 class when we describe domains and ranges, particularly in second semester where we saw lots of different function types and we're definitely interested in domains and ranges. So let's just look at some examples. So let's say the set of numbers we're going to describe are all the x's that are less than or equal to 2. So when I think about doing this here, the first thing I want to do is make sure that I'm clear about what numbers it is that we're talking about. So the things that are less than or equal to 2 would be like 2, like 1.75, 1, 0.0126, negative 24, negative 10,856.27153, etc., all the way down, right? Everybody's cool with what we mean there? So if I think about that then, the first thing I need to do is come up with a lower bound for that set of numbers. The lower bound should be something that's smaller than or equal to everything in that set. So in this case, because we have x is less than or equal to 2, if we pick a number that's less than 2, we can always find another number smaller than it, right? Everybody agree with that? So the lower bound here is not going to be a specific number, but it's going to be negative infinity. Is everybody okay with that idea? Okay. So that's going to be my lower bound. My upper bound here needs to be a number that's greater than or equal to everything in the set. It should be 2, right? Because 2 is the biggest number that could be in that set. It's bigger than or equal to everything in there. Now, I'm going to always use a parenthesis on the infinities. The infinities always get a parenthesis, always. Those are easy. You just have to remember that. The 2 is going to get a bracket because 2 is less than or equal to 2. So it's a member of that set. It should be included. It gets a bracket. Questions so far on anything we've doing? Again, if you can't read something or you need me to slow down or repeat something or you're not sure or you have some other kind of question, stop and ask. If you have a question, I'm sure other people do too. Possibly the same question. Okay, so there's no harm in doing so. I'm going to try to make sure, especially early on, that I'm going at a very reasonable pace. I don't want to leave anybody behind here, especially at the beginning of the year. But if something you're not sure about it or whatever, don't let that stuff go. Just speak up and ask about it. So this next example is the compound inequality. Oh, I'm sorry. Before we start this one, I want to say one other thing about the previous example. My apologies. So this is what we would have done in Algebra 2. We would have written our answer something like this, right? We're going to try to be a little bit more specific here in this class, and that's typical as you go through mathematics, is we don't hit you with the most precise notation all at once. We're going to hit you with okay, this is an acceptable level your first time through, and then the second time you see it, okay, but really we should be doing this also and add a little bit more to the notation and kind of until we get to the most precise representation. So what we're going to also include here in this set is saying, okay, this set is representing what variable? So in our example, that was x's. And so I want the x's are a member of that set. So that symbol there is like an E, but instead of having corners, it just rounded off, is what that symbol is. But that symbol just means x is a member of this interval, this set, is all that's saying. Because the next problem, instead of using an x, what are we going to use?
Y.
A y, because the variable in the next example is a y. So this one will start with y is a member of the set. Everybody's okay with that notation? Just a little bit extra on these to make sure we're being specific. As we remember from Algebra 2, the domains are x's and the ranges are y's. So it's another way to make sure that we're clear about this interval I've just written down is for domain or range, right? Without having to label domain or something. It's just a more precise way of doing that. Okay, so if we look at that next example, -5 is less than y, and y is less than or equal to 10. This is a compound inequality. This is an and inequality where y has to satisfy both inequalities. It has to be greater than -5, and it has to be less than +10. So the numbers we're talking about are like -4.9, 0, 1, 5.7, 9.99999, 10. Everybody cool with what we're representing here? Okay. So the lower bound for this should be -5. Now notice that -5 is not less than or equal to -5. That's okay, because it is smaller than everything else that is less than or -5, right? Okay. The upper bound here would be 10. Now, since -5 is not less than -5, like when I plug -5 in for y, it doesn't satisfy that inequality. It's going to get a parenthesis. And because 10 is less than or equal to 10, when I plug 10 in for y, that one's going to get the bracket. And sometimes I want to be clear, the parentheses and bracket could be the same. They could be bracket, bracket, or parenthesis, parenthesis, or they could be one of each, right? It just depends on the example. Joe.
So basically, does the sign let us know if we're using a parenthesis or a bracket?
The inequality symbol?
Yeah.
Yes.
Excuse me, the symbol.
That's all. Yeah. Yes. You can interpret it that way also. Yeah. The strict inequalities are parentheses, and the or equal to inequalities are brackets.
Okay.
Yep. We'll do one more example here. This will be another compound inequality, but this will be the or inequality. So let's say a is less than -2, or a is greater than or equal to 5. So the numbers we're talking about here are things like, -2.1, -5, -12, -1 billion, or things like 5, 5.7, 6.3, 22, 55 trillion, whatever. Everybody okay with that? So because I have two distinct categories that I have, and I could satisfy either one, I don't have to satisfy both of them, I'm going to write this as two separate intervals. I'm going to write one interval for the first inequality and one interval for the second inequality, and then I'm going to use a symbol in the middle to connect them. I'll show you that symbol in a moment. So let's start with a is less than -2. We'll write a separate interval for that. What is the lower bound for that interval? Jack?
I was just going to ask a question.
Yeah, go ahead.
Do we have to write A as represented?
Oh, A is a member of? Yes, we should start with that. Yes, absolutely. And then I think I heard a couple people say that the lower bound was going to be -infinity. That's right, because since we're talking about the things that are less than -2, you can always find something smaller than -2, right? No matter what number you name, I can tell you something smaller than that number. We can do this forever. The upper bound for A is less than -2 is -2. Now we know the parentheses or the infinities always get a parenthesis. What should the -2 get? Parenthesis also. Good. And then the symbol we're going to use to connect them is going to be this symbol, which is like a U with no tail on it. That symbol is called the union symbol. Not important that you know the name for it, but what it represents, it's really the same thing as or for the language of sets. So that's all that's really saying. So now let's do the other half, or the other inequality. So a is greater than or equal to 5. The lower bound on that should be 5. Good. And the upper bound? Positive infinity. I like to write positive infinity. I wouldn't mark it wrong if you just wrote infinity. I would mark negative infinity wrong if you wrote just infinity, though. Everybody's cool? I like to be specific, so I like to put the positive infinity. It helps make sure that I write the negative ones because I write something in front every time. I'm just used to doing that. But it wouldn't be wrong if you omitted the positive on the positive infinity. Okay, the 5, should it get a bracket or parenthesis? Bracket, good, because it's an or equal to. And the positive infinity always gets a parenthesis. So we're good there. Yes, sir. Of course. No problem. Questions so far? We're doing okay? All right, cool. Let's talk about some domains specifically, since now we've talked about how we're going to write our sets. And here we're going to see a concept that we don't really talk about in our Algebra 2 class, at least directly. So we're going to talk about implied domain versus relevant domain. So the relevant domain would be the things that we would ask for in our Algebra 2 class. So like if I asked you find the domain of y equals, 2x plus 5 divided by x plus 7, that would be a relevant domain question. An implied domain is we would get from the context of the question. So if we look at that same example I just talked about, like y equals 2x plus 5 over x minus 3 or whatever I said before. I don't even remember if those were the same numbers, but like it doesn't really matter. That probably has no context to it, right? It's just a just some function that I stated. In that case, the implied domain is just going to be all real numbers, right? There's no context to it. If there's no context to the problem, I assume, okay, well, there'd be no reason we're in math class. I couldn't put any number I want into this. If there is a context provided, let's say that we have the equation f of x equals x, where x is the number of people needed to screw in a light bulb. That problem has some context to it, right? If x is representing a person, we can't really have negatives because negative people doesn't make any sense. You can't really have like fractions or decimals because like 7/8 of a person, what the heck does that mean? Right? That doesn't make any sense. So there, our implied domain would just be like our positive whole numbers, or non-negative whole numbers, I should say. So like 0, 1, 2, 3, 4, but no decimals in between them, right? Because we're talking about people. X is representing a person. Does that feel okay there with what I mean by an implied domain? It's just based on the context of the problem. And if you're given no context, the implied domain is just all real numbers. Now, these two are related because the relevant domain is always going to be a subset or equal to the implied domain. So the relevant domain is always going to be the same size or smaller than the implied domain, never bigger. So it's always going to be a little bit more precise. And we'll do some examples now with numbers so that we can kind of practice getting the hang of these two concepts. In general, the implied domain is something that really comes up in like a story problem where there's some context to what it is you're working with. If there's no context, if there's no words, the implied domain is just like all real numbers, so it's kind of trivial. So here we're just going to write the domains for these functions using interval notation. Is kind of the direction that we're going to use here. So here we just have f of x is equal to 2 times the square root of x minus 4. So here, the implied domain, there's no context given. So the implied domain is just all real numbers, right? Not very interesting. Now, I would prefer that we, in this course, that we're using like the more precise notation. That's why I chose to write it this way instead of just writing ARN, which was acceptable the first time we see interval notations. But here I'd prefer to be a little bit more precise. Okay, so the relevant domain, to figure that out, I'm going to have to look at the operations involved in my function. So my function, 2 times the square root of x minus 4. I see 3 distinct operations going on. I see multiplication because I have 2 times something. Everybody agree? I see subtraction because I have x minus 4. And I see the square root. So 3 operations. Everybody feel okay identifying those 3? Okay. So now what I want to do is I want to think about, okay, if I have 2 real numbers and I subtract them, is there any way that I can get something undefined? Would I fail to get an answer subtracting 2 real numbers together? No, right? Real number minus real number, you're always going to get something back as an answer, right? Okay, what about if we do multiplication? If I multiply 2 numbers together, I'm always going to get a result? Yeah. What about the square root? If I take the square root of a number, am I always going to get an answer?
Oh, yeah.
A real number answer.
Not a negative every time.
Yeah, not a negative, right? Remember what happens when you take the square root of a negative? We get an imaginary solution, right? So that's the place where I have to worry about with my relevant domain, is all this stuff that's underneath the square root has to be non-negative, right? Has to be at least 0, or else I wouldn't be able to take the square root of it. Is that okay with everybody? Okay. So what I'm going to do now is I'm just going to solve this inequality. So I'll add 4 to both sides. So again, x is greater than or equal to 4. And now I'm going to just write that inequality as a interval notation, and I'm done. So x is greater than or equal to greater than or equal to positive 4. The lower bound is 4 with a bracket. Good. I lost my pen again. Where'd you go? There you go. Okay. And the upper bound is positive infinity, and those always get a parenthesis. So notice that that interval is smaller than all real numbers, right? Because we've lost everything that's less than 4. But it's still a subset, right? It's part of the real numbers, just not everything. Okay, let's do another. Well, we'll do 2 more, actually. This one and the next, and 1 more after that. Again, no context was provided for this problem. It was just like a function that we wrote down. So I know the implied domain is just all real numbers. Not very exciting. The relevant domain now, I'm going to look at the operations involved in this function. What operations do we see?
3 times x.
So multiplication, division, and addition. Very good. So multiplication we already established isn't a problem in the previous problem, right? How about if subtraction wasn't a problem, is addition going to be a problem? No. What about division? What gets us in trouble dividing? Where would we fail to get an answer? If you divide by 0, right? We know that if we divide by 0, that's undefined. So that's the place that I have to worry about. I know that division is this, or the divisor of a division problem is the same thing as the denominator of a fraction. So all I'm going to do is I'm going to take that denominator and set it not equal to 0. Any other value for x is going to be fine, other than whatever gives us 0 for x plus 2. So I'll go ahead and solve that. I'll subtract 2 from both sides to get x is not equal to negative 2. And now I'll try to write my interval. The problem is I don't have inequalities here, right? I have this not equal to. So what I'll do is I'm just going to rewrite that not equal to as an inequality. So let's think about the numbers that are not equal to negative 2. That would be all the x's that are less than negative 2, or would be all the x's that are greater than negative 2. Right? That's everything that's not equal to negative 2. Did you guys buy that? So that's a nice little trick to turn a not equal to into an inequality. And now that it's written as an inequality, we can handle this with interval notation, right? So if I look at x is less than negative 2, my lower bound is negative infinity. The upper bound is negative 2. And then what do I get on the ends here? For both. Now, because of the or, I'm going to do that union symbol again. And then for x is greater than negative 2, the lower bound is negative 2. The upper bound is positive infinity, or just infinity is fine. And the ends get parentheses in both places. So if you look at that again, that's like everything except for negative 2. Which again, in your Algebra 2 class, we probably said it was fine for you to just write like ARN, comma, x not equal to negative 2. Here we're going to ask you to be a little bit more precise and use interval notation kind of all the time, and not some of these that are like, okay, you've communicated this accurately, even though the notation is like, you know, kind of suspect or whatever, not very formal. Informal would be the name for not very formal. Last example here. So let's say v of s is equal to s cubed, where v of s is the volume of a cube with edge length s. So here we have some context, right? So this is a place where we have to be a little bit careful when we're figuring out our implied domain. So again, if we're talking about a domain, we're talking about the independent variable. I can tell from the function notation that s is our independent variable, right? In our sentence there, what is s representing? The edge length for a cube, right? So an edge length of a cube can be what kinds of numbers?
0.1 to infinity.
It has to be a positive number, right? And here is a place where, you know, like, depending on how you've defined a cube, maybe even 0 is an acceptable edge length. it would depend a little bit on like what the formal definition of a cube is that you're working from. For the sake of our argument, I'm going to assume that like a zero edge length cube that's essentially a single point is still counts as a cube, depending on how you define things. So I'm going to say that's okay. So here we're really talking about 0 to positive infinity, right? Any kind of non-negative value for s is a valid edge length for our cube. Everybody cool there? Yes, sir. Of course.
Why did you include 0?
So here, I wouldn't mark it in this problem with what's been given to you. I wouldn't mark it wrong if you didn't. Because here it's not, I didn't give you the definition of a cube, whether that definition should include a 0 side length figure or not. I'm going to just choose to include it to come up with an answer, but I wouldn't mark this wrong with what I gave you if you did not. Is that?
I just don't, how can you ever, the cube doesn't exist beside 0.
Right, but could that be valid if you're calculating a volume? That would have 0 volume, right?
Yeah.
Still, so maybe that's still a valid response. Like it's one of those where like it's not, the definitions aren't quite precise enough to like say one way or another what you should do. I wouldn't mark it wrong either way with what I've given you. But I'm just going to say for like the sake of writing an answer down, I'm going to pick to include that. Yeah. So like, okay, so something that's not there is a 0 volume. Should that be included in our function operation? Do I want to have something that has like no volume left to it? Probably, like in a real world setting, you probably want that. Whether it, I don't know. It's like something we could sit here and argue about it for an hour and not come up with a reason why one is, whole list of reasons why one makes sense and the other does not. Or why both of them makes, the same amount of sense either way. Anyways, now to work on our relevant domain, let's look at the operations involved. I see just really one operation. What do you guys see? What is the operation? Yeah, multiplying, which is cubing is really just multiplying the same thing 3 times, right? S times S times S. Is multiplication a problem? No. So our relevant domain should be the same as the implied domain. And if you had looked just at the function, though, you would have said, oh, the domain should be all real numbers if you didn't factor the context into it. So that's my example of where the implied domain really matters. You know what I mean? But it's really just like a story problem situation. We doing okay? Do you want to take a minute, stand up and stretch out? I know it's 8th hour, and I see that some of us are fading a little bit. Do you want to take a minute? We good? Okay, that's fine. I just thought I'd offer. I get it. An hour, whatever is a long time to be sitting here doing math. What we're going to talk about next is finding ranges. So ranges are almost always going to be more difficult to obtain than the domains, because the ranges are built on the y-coordinate, which is the dependent variable. So it really depends on our answer for the domain. Now, when I try to do this algebraically, what I like to do is to look at my function and figure out where is the function increasing and decreasing at. So if you think back to our Algebra 2 class from last year, let's say that this is our function f of x that goes from x-coordinate A to x-coordinate B. Notice that one of them is open because that point is not included. I'm just doing that for example purpose here in a second. That's an example of an increasing function, right? Because as you move from left to right, the line kind of heads up. Everybody okay with that? And then let's say that we have another one that goes from point C to D. Let's call this one g of x. And this one, since as you go from left to right is heading down, is decreasing, right? So far, so good. So if I look at this function g of x, the domain here would be just from C to D. Again, C is included because that circle is filled in. D has the parenthesis because that circle is not filled in. Similarly, for the red, the domain would be A to B. Again, A gets the bracket because the A circle is filled in, and B gets a parenthesis because the B circle is not filled in. Now, if I want to do the range, the lower bound for the range is going to be the smallest y-coordinate on our function. That occurs at the point whose x-coordinate is A. Everybody agree with that? You know, it's happening right here. That's the lowest point on the graph, right? That should be the lower bound. The y-coordinate there should be the lower bound for our range. The way we write that y-coordinate is f of A. And because A got a bracket, f of A is going to get a bracket. The upper bound would be the y-coordinate at B. So that would be f of B. And again, because B got a parenthesis, f of B is going to get a parenthesis. Joe? Of course. Now, if I look at the decreasing function and want to do the range, here the lower bound is at the point D, right? That's the lowest point on the graph, so the smallest y-coordinate. So that would be, the y-coordinate there would be f of D. And because D got a parenthesis, f of D should get a parenthesis. And the highest point on that function is C. So the y-coordinate there would be f of C. And because C got a bracket, f of C gets a bracket. So the takeaway here, what we're going to use is if I know whether my function is increasing or decreasing, I know how to find the range on that increasing or decreasing interval. I just look at the endpoints of the function, of the domain at that, right? I can just evaluate the endpoints using my function. So let's do some examples, because this looks kind of complicated right now, and it turns out it's not so bad. Is everybody ready for this? Okay. So I'm going to use the same three functions that we found the domains for, and I'm going to include the domains with them in my examples that we just found earlier. Oh my goodness. I am not writing the right thing. Sorry about that. So my first thing I want to figure out is this function, 2 times the square root of x minus 4, is this thing increasing or decreasing? And then if it's just one or the other, great, I can go straight to finding my range. If it's part increasing and part decreasing, then I have to figure out, like, okay, where does it switch, increasing to decreasing? Now, ideally, you would remember from your Algebra 2 class last year, the general shape for a square root function like this, because we graphed them. I'll take a moment and just talk about that, assuming that you did, even though I know that's wishful thinking on my part. So they're going to look either like this or like this. Do you remember how you can tell the difference between something that looks like the red one and something that looks like the blue one?
One of them is negative.
Yeah, the leading coefficient is positive for the red one, and the leading coefficient is negative for the blue one. So in our case, the leading coefficient here is the 2. So we have a situation like the red one. So we know that we are increasing. Now, if you didn't remember that from your Algebra 2 class, what else could you do to figure out the shape of the graph to tell if it's increasing or decreasing? Graph it on your calculator and take a look at the picture, right? It's still valid. It's okay. Okay, so since this is increasing, I know that the lower bound for my range is just going to be f of the lower bound for my domain. And the upper bound for my range is going to be f of the upper bound for my domain. Actually, let's do this since these are notes. I'm going to put a little r there, and I'm going to put a d there, and then I'll write f of 4 and f of infinity. Everybody okay with the notation that I'm saying? Like the lower bound for the range is f of the lower bound for the domain. Is that cool, the notation there? That maybe helps if you go back and look at this. Okay. So f of 4, that's easy to do, right? Just plug 4 in for x. So that gives me 2 times the square root of 0, which is just 2 times 0, which is 0. Good with that? The other one is going to be a little bit weird, but it's going to be okay. We're going to have to use a little bit of common sense because, like, what am I doing here? I'm plugging in an infinity or something. Come on. There we go. But that's okay. Riley? Of course. You're welcome. Okay. So here we're going to have to use a little bit of common sense because you can't really do arithmetic with an infinity on there. But if I have infinity and I subtract 4 from it, what do I have? If you infinitely many things and you take 4 of them away, it's still infinite, right? Now, if I have infinitely many things and I take the square root of them, it makes it smaller, but does it make it less than infinitely smaller? No. And if I have infinitely many things, I multiply it by 2. It's still infinite, right? Now, I need to figure out the sign on my infinity. Since this is an upper bound, the sign on the infinity must be positive. If it were negative, it wouldn't make any sense because you'd be saying, okay, I go from 0 to negative infinity. Well, there's no numbers in between that are bigger than 0 and less than negative infinity, right? So that's like a little self-check. So what we'd say is then y is a member of this interval from 0 to positive infinity. And because we use the 4 here, and the 4 gets a bracket, and the 0 comes from plugging the 4 in, the 0 gets a bracket. Likewise, the infinity gets the parenthesis. Is that okay with everybody? Yes. Of course. You're welcome. Okay. Next up, we have the g of x equals 3x over x plus 2. So again, ideally we remember back from our Algebra 2 class, this is something where, okay, I recognize this as a simple rational function, so it's going to have like a vertical asymptote and a horizontal asymptote. Doesn't really matter where they are. And then the graph is either going to have like these two hyperbolas, but they're always going to be like kind of kitty corner from one another. So it'll either look like that, or it'll look like this. And the way you can tell is you get the green situation when the leading coefficient of the top over the leading coefficient of the bottom is negative. And you get the blue when the leading coefficient over the leading coefficient. Oh, I switched those. My apologies. Sorry. The blue is when the leading coefficient is negative, and the green is where it's positive. My apologies there. So here, come on. Come on. Where's my pen? Why are we being so needy today? Okay. Sorry, I'm just frustrated by... I'm going to apologize in advance for my infinity symbols here, because doing this with the mouse is much harder and like agonizingly slow for me. Okay. Sorry, I forgot to write this initially. So this is not part of the computation. This was just part of the original problem. Okay, so when I look, the leading coefficient on top is 3, and the leading coefficient on bottom is 1. So we're in this situation. Everybody good there? When I look at this piece, there we're going down as we move from left to right. So this first interval, we're going to be decreasing. And when I look at this part of the graph as I move from left to right, also we're going down. So this piece is also decreasing. Does that feel okay with everybody? Yes, sir. Absolutely. Okay. And now I really regret not having...
You want to use my pen?
Yeah, do you mind?
Yeah.
Thank you. All right. So now it works perfectly. So what we're going to do, since it's decreasing, the lower bound for the range, and I'm put a 1 here also since there's 2 parts of the range, is going to be g of the upper bound from the domain, it's first part. The upper bound for range 1 is going to be g of the lower bound for the domain 1. And then the lower bound for the second part of our range is going to be g of the upper bound for the second part of the domain. And the upper bound for the range 2 is going to be the lower bound from the domain 1. Remember, when it's decreasing, they're flipping, right? So lower goes to the upper and upper goes to lower. When it's increasing, they're the same. Okay. Oh boy, that jumped way out of the way that I wanted it to. Sorry about all the moving. I know I get car sick when people are moving the screen around that fast on me. All right. So here we're going to do g of the upper bound. So that was -2. So when I plug that in, I end up with -6/0. When you divide by 0, we say the answer is undefined because really the answer is infinite. So if you think about when you divide something in half, you get 2 pieces. If you divide something into 0 piles, like you've chopped it up so finely that there's nothing left. It's like really your infinitely many cuts that you have to make or whatever. So the question becomes, is this positive or negative infinity? Since it's a lower bound, it's got to be negative. So lower bounds, if you get an infinity, always negative. Upper bounds, if you get an infinity, always positive. If we do the same thing here, g of negative infinity is 3 times negative infinity over negative infinity plus 2. So I have 3 times negative infinity on top. Negative infinity plus 2 is still just negative infinity, right? As we established earlier. Now 3 times negative infinity over negative infinity just 3. Yes, sir.
So if one of the infinities was positive instead of negative, can you still cancel them out or no?
Mm-hmm.
Okay.
Yeah, they would still be fine. You'd end up with a negative sign also, but you can still do that same thing.
All right.
And now down here, this is going to just be g of negative infinity, which we already know is 3 from above. And this is going to be g of -2, which we already know is -6/0, or some kind of infinity. And because this is an upper bound, we know it has to be the positive infinity. So piecing this all together now, we have y is a member of negative infinity to 3. And because if I go back to the domain, each of those were parentheses. Each of these will be parentheses. And then I have union 3 to positive infinity. And because when I go back to the domain, each of those were parentheses. Each of these will be parentheses. And I think we're out of time here. We still have 2 more minutes or something. We have enough time to do the last one because it's very easy, which is nice, right? So this one, if I think back to what the graph of x cubed would have looked like this, which is increasing the whole way. So our lower bound for the range is just going to be v of the upper bound, lower bound for the domain, and the upper bound for the range is going to be v of the upper bound from the domain. So that's v of 0, which is just 0. And that's going to be v of infinity, which is infinity cubed, which is just still infinity. And since this is an upper bound, we know the infinity is positive. Everybody good there? So v of s is 0 to positive infinity. The positive infinity we know gets a parenthesis. And because the 0 that we used as the input had a bracket, we know the 0 that we get as an output also has a bracket. That's done for today. The homework, the first homework set is just 1 through 12. So if you go and you look at the problem set is also in the content library. So just 1 through 12. You can do your homework in OneNote, that's fine. If you do that, please do it like on a separate column, so in like number things and like show some work, and don't just try to cram it in like right next to the question. Please, 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 please. If you choose to do your homework by hand on paper, totally fine. Just take a picture when you're finished and dump it into your homework folder on OneNote. Okay? Joe, I need to give this back to you. You're welcome. And Ellie and Stephanie, if I can see you guys for a few minutes before we take off.